Okay, so we've just started chapter 11, and we're going to do canonical quantization of the free field. Now, what canonical quantization is, it's the standard way to do quantization. So canonical means the usual or the standard or the conventional way, and quantization means to turn a classical theory into a quantum theory. So what we're doing now would be the standard way to turn any classical theory that you have into a quantum theory. So you should think that we're illustrating a very general method. What theory do we want to quantize? Well, the theory we want to quantize is described by this Lagrangian density that we have already explored in a little bit of, well, we did a few things with it. Okay? So that's the form of the Lagrangian density. And then we just perhaps rewrite it in a way that will be useful for us. So those first two terms that I've written down are just the kinetic terms from the Lagrangian density. So that single term becomes those two terms. And I'm using a very standard notation, but let me spell it out. So as usual, phi dot is equal to d phi dt. Good. So that's the form of the Lagrangian density. And what we want to do now is we want to obtain the Hamiltonian description. Okay, so you'll usually be given a Lagrangian because it's simplest to construct Lagrangians. You can use your knowledge of symmetry to construct the Lagrangian, but then to quantize, at least using canonical quantization, we want to obtain the Lagrangian, the Hamiltonian description. So the first thing that we need to do, we need to calculate the conjugate momentum at x and t. So this is a field, and it's given by the derivative of the Lagrangian density with respect to x and t. And looking at the Lagrangian density given above, it's the first term underlined in red that makes a contribution, and we just get phi dot of x and t. And then, as usual, the Hamiltonian density is related to the Lagrangian by a Legendre transform, okay? And what are we doing here? Well, we're swapping out a function that depends on phi and phi dot for a function that, sorry, let me just, for a function, the Hamiltonian density that depends on phi and pi, okay? So this is the completely usual thing. This is why we use the Legendre transform. And if we work out what is pi phi dot minus L, we've done this, so I'm not going to do it again. This is 1/2 pi squared plus 1/2 the gradient of phi dotted into the gradient of phi plus 1/2 m squared phi squared. Okay, once you've got the Hamiltonian density, you can easily write down the Hamiltonian. The Hamiltonian is nothing but the integral, d3x of the Hamiltonian density. Good. Okay, so maybe let's just talk about what is the interpretation of these terms. Well, this first term over here is telling you it costs energy. Okay, it's a positive term, contributes positive to the energy to change field values in time. So as soon as your field has some time dependence, pi will be non-zero, and then it will cost you some energy. The second term over here, the 1/2 gradient of phi dotted into the gradient of phi, tells you it costs energy to change the field values in space. So if you've got one value of the field at x, and you want to change it to a different value of the field at some nearby point x plus epsilon, well, of course, that means you make the derivative with respect to x non-zero, and that costs you energy. And then the last term tells you it costs energy to have even a constant field. Okay, so the first term is telling you the cost of having the field change, in the field's value change in time. The second term tells you the cost of energy to have the field's value changing in space. And the last term tells you the cost to have the field around at all. We know that the field will obey some Poisson brackets. We've discussed these in detail. So let's just write down what these Poisson brackets are. X minus y. And the Poisson bracket of the conjugate momentum with itself vanishes, as does the Poisson bracket of the field with itself. So the only non-vanishing Poisson bracket is between the field and the conjugate momentum, and that simply gives you the Dirac delta distribution. To quantize, okay, so by the way, this is completely standard. I could have given you any Lagrangian density. You could have gone ahead and calculated the conjugate momentum and then the Hamiltonian density, and you could have written down the Poisson brackets. To quantize, you need to promote the Poisson brackets to commutators. And you do this using Dirac's correspondence principle. So what did Dirac give us? He gave us a principle by which we turn any classical theory into a quantum theory. And what does Dirac's correspondence principle tell us? Well, the commutator is exactly the same as the Poisson brackets. All you need to do is multiply by I h bar. So that's the commutator between the field and its conjugate momentum. And then the commutator between the conjugate momentum and itself vanishes. And the commutator between the value of the field and itself vanishes. So this would be a complete set of commutators. These are the equations that you would solve to figure out what your operators are. So by solving these commutators, you'd figure out what pi and phi are. Then, of course, we also need dynamics in the theory. But you know that in terms of Poisson brackets, the equation of motion for any observable O is just given by the Poisson bracket of O with the Hamiltonian. And after promoting this to an operator equation, we get nothing but the Heisenberg equation of motion. So I've given you the equations that specify the operators, and I've given you the dynamical equations. So here's the important equations. These define the operators. And then the equations of motion of the theory given by the Heisenberg equations of motion, and the Hamiltonian is given as an integral of the Hamiltonian density. Good. Okay, so that's how we quantize. Now, I want to give you a little exercise to make sure that you've understood it. Let's imagine that we study n free scalar fields. So in this situation, what the Lagrangian density would look like, there would be, in fact, let me write it like this. There would be a sum from A is equal to 1 up to n. Then you would have 1/2 d mu phi A minus 1/2 m squared phi A squared. So one term for each A, one Lagrangian for each of these fields, If you go ahead and calculate what is the Hamiltonian density, so please verify this answer, make sure you can get it. I claim it's a sum from A is equal to 1 to n of 1/2 pi A of x and t. Let me not indicate that. Pi A plus 1/2 gradient of phi A into the gradient of phi A plus 1/2 m squared phi A squared. If you go ahead and you calculate what is pi A equal to, this will be equal to phi dot A. And if you were to go ahead and calculate what are the Poisson brackets, the Poisson brackets that you find would tell you that phi A of x and t and pi B of y and t are equal to delta AB delta x minus y. And the remaining Poisson brackets, let's just write them down. So if we took pi A of x and t and pi B of y and t, this would vanish, as would the Poisson bracket between phi A of x and t and phi B of y and t. That Poisson bracket would also vanish. And then you could promote these Poisson brackets to commutators, and you would again have the quantum theory, but now of n free scalar fields, okay? And let's maybe just write down one commutator. So phi A of x and t and pi B of y and t would be, well, I need an I h bar delta AB delta of x minus y. And the remaining commutator between phi A and phi B would vanish, and between pi A and pi B would vanish. And that would then be the theory of n scalar fields. And I just applied exactly the same recipe as I used to quantize a single scalar field.